Tokyo, spring, 1945. In a dim hangar on the outskirts of Tachikawa Airfield, a strange silence fills the air. Under the flicker of weak electric lamps, a group of Japanese engineers in oil-stained uniforms circle a captured American fighter. Its silver skin glints faintly beneath tarps torn by wind, the letters P-51 stenciled in fading paint. The air smells of fuel and metal. Someone runs a gloved hand across the smooth, riveted fuselage, tracing the foreign workmanship. Beside them lies a clipboard filled with numbers: fuel capacity, manifold pressure, range radius, figures that stretch beyond anything their own fighters could reach. They measure, they disassemble, they take notes in precise handwriting. But as hours pass, the quiet turns heavier. The numbers don't lie. No matter how carefully they calculate, the truth is the same. Japan cannot match this machine's reach, nor the industrial miracle behind it. That realization, born in a silent hangar, marks the beginning of the end for Japan's control of its own skies. The air war tightens. 1943-1944. By 1943, Japan's air empire was shrinking faster than its engineers could replace it. Once the rising sun had stretched from Burma to the Solomons, defended by the nimble Zero and Kai-43 Hayabusa. But the balance of the Pacific Air War was turning. The early brilliance of Japan's pilots and aircraft designs, lightweight, long-legged, and agile, was colliding with the Allied machine of mass production and innovation. In the skies over Rabaul, New Guinea and the Central Pacific, Allied aircraft were appearing in greater numbers and with new technology: better armor, radar, self-sealing tanks, turbo-superchargers. The Japanese fighter force, built for range and maneuverability, found itself outclimbed, outdove, and increasingly outnumbered. Worse still, its veterans, the irreplaceable cadre of pre-war flyers, were dying faster than they could be trained. By mid-1944, American industrial power had reached its stride. B-24 Liberators and B-29 Superfortresses were rolling off assembly lines in thousands. Each bomber demanded escorts that could accompany them across oceans and back, a requirement that birthed the long-range fighter. In contrast, Japan's aircraft industry was fracturing under shortages of aluminum, precision machine tools, and aviation gasoline. Japanese refineries struggled to produce high-octane fuel. Pilots often flew with lower-grade mixtures that robbed engines of power and reliability. Even the vaunted Nakajima and Mitsubishi engines, impressive on paper, suffered from weak superchargers and inconsistent metallurgy. The engineers understood the problem. To fight the new war at high altitude and over long distances, they needed both advanced power plants and fuel of a quality Japan's resources could no longer sustain. In America and Britain, research labs solved such problems by the hundreds each month. In Japan, the process was reversed. Engineers adapted to what remained. They lightened airframes, trimmed fuel loads, and simplified production, all while the front lines moved ever closer to the home islands. Through 1943 and early 1944, the U.S. Navy's island-hopping advance tightened the noose. With each new airfield seized, the Allies shortened the ocean that separated their bombers from Japan. Saipan and Tinian became springboards for the B-29 offensive, their long concrete runways symbols of America's logistical triumph. When the first silver bombers appeared over Kyushu and Tokyo in late 1944, Japanese commanders confronted a new kind of war. One fought at the edges of range and endurance. The Imperial Japanese Army Air Force, IJAF, and Navy Air Service scrambled to respond. New interceptor designs like the Kai-84 Hayate and the N-1K2J Shidenkai promised improved climb and firepower, yet their performance was throttled by production delays and engine defects. None could escort bombers across the vast Pacific or sustain high-altitude flight for hours. Meanwhile, across the ocean, a slender aircraft with a laminar flow wing was redefining what fighter meant. The North American P-51 Mustang, originally built to British specifications, had evolved from a modest ground attack plane into a transoceanic escort weapon once it received the Packard-built Rolls-Royce Merlin engine. With its efficient aerodynamics, internal fuel, and detachable drop tanks, it could fly more than 1,600 kilometers and still fight when it arrived. That range would prove devastating. The Mustang's combination of speed, altitude, and endurance meant that American bombers could now strike Japan's war industries by day and return with acceptable losses. It also meant that Japanese interceptors, limited by short legs and dwindling fuel, could not choose when or where to engage. They were forced into desperate climbs and brief attacks before turning for home. By late 1944, the Japanese High Command recognized that range, not agility, had become the decisive metric of survival. Reports flowed from the front. Enemy fighters appeared farther from base than expected. Bomber formations were escorted all the way to target. Each report carried the same quiet dread, a technological gap widening beyond repair. Inside Japan's technical bureaus, engineers began requesting any captured Allied aircraft for study. They hoped to decode what had changed in the West's aeronautical thinking. The request was urgent, almost pleading. Find one of these new long-range machines intact. When a P-51 finally fell into their hands, damaged but largely complete, the moment felt like an opportunity to reclaim lost ground. Yet as 1944 turned to 1945, the nation's factories were in ruins, its resources bled dry, and its sky filled with bombers the Mustang protected. And so, under the roar of distant air raid sirens, Japan's engineers prepared to study the fighter that had made invasion inevitable, Iwo Jima Taken. VLR Escort arrives by early 1945. Japan's defensive map had collapsed into concentric rings around its own homeland. The U.S. Pacific advance, planned with clockwork precision, had reached the volcanic ridgeline of Iwo Jima, the last island fortress between the Marianas and Tokyo. For American planners, this patch of black sand was more than a symbolic foothold. It was a runway. Iwo Jima's capture promised a base for very long-range fighter escorts, aircraft that could meet B-29 formations from Saipan and Tinian halfway to Japan, fly with them to target, and return. The Battle of Iwo Jima began on February 19, 1945, and cost nearly 30,000 American and Japanese lives. When the final guns fell silent in March, engineers from the U.S. Army Air Forces began carving airstrips out of sulfuric ash. By mid-spring, concrete runways stretched across the island, and fuel tanks gleamed under camouflaged nets. From those runways would rise the 7th Fighter Command, the Mustang units of the 15th, 21st, and 506th Fighter Groups. Their orders were unprecedented. Escort B-29s all the way to the Japanese mainland, nearly 1,500 miles round trip. The pilots called it VLR, very long range, a new art of flight that demanded as much from engine and fuel system as from flesh and nerve. Each mission was an exercise in mathematics and discipline. Drop tanks of 75 and 108-gallon capacity hung beneath the wings like lifelines. The pilots set mixture controls to lean cruise, climbed on fractional throttle, and calculated each gallon burned as the Pacific unrolled beneath them. The Mustang's Packard Merlin engine, with its two-stage supercharger, could breathe at altitudes where Japanese interceptors gasped. Combined with the aerodynamically efficient laminar flow wing, it delivered a harmony of power and endurance that no Axis fighter could rival. On April 7, 1945, the first VLR escort mission lifted off from Iwo Jima. B-29s headed for the Nakajima Engine Works near Tokyo, and Mustangs rendezvoused with them 700 miles from base. Japanese observers on the coast watched astonished as American fighters appeared over Honshu, escorting bombers from horizons once thought unreachable. Reports flooded command posts, enemy fighters accompanying bombers to target. For Japan's air defense network, that single sentence meant the rules of air war had changed. Radar stations struggled to track incoming formations. Fuel shortages limited the number of available interceptors. When they did scramble, pilots faced enemy fighters still fresh, engines tuned for altitude, guns ready. The encounters were brief and brutal. Where Japanese interceptors once counted on Allied bombers appearing unescorted, they now found themselves ambushed by agile Mustangs that waited in the thin air above. For Tokyo's defense planners, the implication was catastrophic. The Mustang's range neutralized Japan's geographic advantage. Its homeland, once protected by distance, now lay within continuous Allied fighter cover. Even the Navy's remaining Zero and Raiden interceptors, capable of sharp climbs and tight turns, could not sustain combat for more than a few minutes before fuel gauges neared zero. Inside Japan's military research circles, anxiety turned to curiosity. How could a single-engine aircraft maintain such range and performance? Engineers from the Army's Tachikawa Air Arsenal and the Navy's Yokosuka Technical Air Command began collecting fragments of downed Mustangs for study. They inspected drop tank connectors, fuel transfer valves, and the intricate routing of coolant ducts. Each recovered part hinted at a sophistication of design that seemed impossible under Japan's wartime industry. Then, late that spring, fortune, or misfortune, delivered an intact specimen. A P-51D crash-landed on Japanese soil after a raid, its pilot captured, its airframe battered but recoverable. The order was immediate: transport it to a secure hangar for complete examination. For the engineers, this was the moment they had waited for. At last, they could see the enemy's secret up close. Yet even as they began their measurements, fuselage fuel capacity, wing root tanks, drop tank plumbing, radiator design, reports from Iwo Jima told of new waves of Mustangs now strafing Japanese airfields at will. The enemy's long reach was not theoretical. It was operational, daily, lethal. In that paradox lay the quiet tragedy of Japan's late-war science. Brilliant minds working in isolation, studying a machine that already controlled their skies. The hangar lights at Tachikawa burned late into the night, illuminating diagrams and dismantled panels. Each discovery confirmed what field commanders already knew: that Japan's technology, industry, and logistics could not close the distance between its homeland and the approaching enemy. And as their pencils scratched across paper, one truth became clear. To understand the Mustang was to understand how Japan had already lost the air war. Engineering reality. The two-stage secret when the Japanese engineers at Tachikawa removed the P-51's engine cowl. They expected to find a scaled-up inline motor similar to the Daimler-Benz or their own Kawasaki Hey 40. Instead, they found complexity that bordered on art. The Packard-built Rolls-Royce Merlin V1657 was more than metal and pistons. It was a system. At its heart lay a two-stage, two-speed supercharger, its gears, impellers, and intercooler ducts woven into a compact block. The Japanese Navy's Homar and the Army's Hey 45 engines used single-stage units that lost power rapidly above 20,000 feet. The Merlin held its breath to 35,000 feet, sustaining the Mustang's climb even in thin air. To reproduce that would require high-temperature alloys, machine tolerances within thousandths of an inch, and a stable supply of precision bearings, none of which Japan could mass-produce in 1945. They noted the intercooler's elegance, a web of ducts that balanced temperature and pressure perfectly. Even if Japanese metallurgists could copy the shapes, they lacked the consistency of American manufacturing lines. Every Packard factory engine was nearly identical, every Japanese engine slightly different. War conditions turned individuality from artistry into liability. Engines that ran beautifully on test stands failed in combat because gaskets, seals, or bearings came from overstressed suppliers. As the examiners logged data from the captured Mustang, one officer quietly remarked that the Americans had achieved something Japan once prided itself on: craftsmanship. But they had done it at industrial scale. That realization stung more than any blueprint could explain. B. Fuel and range economy. The invisible weapon. Next came the heart of endurance. Fuel. The engineers drained what remained in the Mustang's tanks and sniffed the sharp odor of high-octane aviation gasoline, around 150 grade by Allied standards. Japan's best fuel rarely exceeded 92 octane. The difference was not abstract. It governed every calculation of mixture, detonation, and supercharger boost. The Mustang's carburetor and mixture control levers allowed precise, auto-lean settings that stretched miles out of every gallon. Pilots were trained to nurse the Merlin for hours, adjusting prop pitch and manifold pressure with scientific precision. Japanese flyers, trained for short-range interception, were taught aggression, not economy. Their engines guzzled fuel during combat climbs, leaving only minutes of endurance. Engineers traced the Mustang's fuel lines like arteries, internal tanks behind the pilot, wing root cells, and quick disconnect fittings for external drop tanks. The plumbing was robust yet simple. No leaks, no wasted volume. They realized that range was cumulative. Not one innovation, but dozens. Fuel grade, pump reliability, airflow efficiency, pilot discipline. They compared the Mustang's systems with their own Kai 84 Hayate. On paper, the Hayate's range approached 200 kilometers. In practice, poor mixture control and maintenance reduced it drastically. High drag from bomb racks and misaligned panels compounded the loss. The numbers mocked ambition. From the engineers' notebooks came a recurring phrase: "Quality of gasoline limits design potential." Even a perfect copy of the Mustang would have been crippled by Japan's fuel. In that sense, the Mustang's real weapon was not its guns but the petroleum empire that fed it. See airframe and drag, the shape of distance. The longer the engineers examined the fuselage, the more they realized how much air itself was part of the design. The Mustang's skin felt smoother than anything built in Japan. Flush riveted, polished, its laminar flow wing holding its exact contour from root to tip. When they placed measuring templates along the wing, they saw how subtle the shape was, a balance between lift and drag that no drafting table could guess without wind tunnel data. Japan had wind tunnels, but not time. Their fighters, optimized for turn combat, relied on thick wings and manual flaps. The Mustang's wing, by contrast, was a time machine. It bought minutes of fuel and miles of range simply by reducing drag. Even the cooling system betrayed ingenuity. The engineers studied the deep ventral radiator duct and discovered the Meredith effect, a thermodynamic trick where heated air exiting the radiator added thrust instead of drag. It was small, a few dozen pounds of force, but over 1,000 miles it mattered. Japanese fighters vented heat wastefully through side ports. They also noted the canopy, clear, teardrop, offering minimal resistance. The landing gear retracted completely flush. Each of these details seemed trivial until added together. What they represented was philosophy, an obsession with drag reduction that extended from screw heads to fuel strategy. When the session ended, the chief engineer wrote a final note. To increase range by 50%, we must reduce resistance by 1/3. Our tools cannot achieve such surface finish. He understood what the others were beginning to accept, that the P-51's range was not a single secret to steal, but 1,000 refinements impossible to compress into the dying months of an exhausted nation. And yet they continued measuring, hopeful that somewhere inside this foreign machine lay a clue that could still save them. D. Navigation and radios. The unseen compass. When the engineers reached the cockpit, they discovered something far more decisive than horsepower: situational awareness. The Mustang's cockpit layout was organized, almost surgical. Each gauge and switch aligned in ergonomic logic. Japanese aircraft, by comparison, reflected a craftsman's hand more than an engineer's discipline. Cluttered, inconsistent, and without standardization between models. At the center sat the SCR 522 radio set, its wiring harness wrapped in labeled insulation. With this device, a Mustang pilot could stay in touch with formation leaders hundreds of miles from home, receive vector corrections from ships or stations, and, critically, coordinate with bombers in real time. Japan's equivalent systems were unreliable, often sabotaged by static interference, and lacked the power output to cover the same distances. Attached to the radio was a radio direction finder loop, a small device that allowed homing on beacons from hundreds of miles away. In the Pacific, this meant survival. Pilots could navigate by coded signals from Saipan, Iwo Jima, or carrier relays, compensating for fog or weather. For Japanese pilots, navigation remained an art of compass bearings, dead reckoning, and memory, a system that faltered under cloud or combat stress. The engineers listening to captured American manuals were astonished by the procedural discipline. The Allied pilot didn't rely on intuition. He relied on systems. The Mustang's range therefore extended beyond fuel. It was the sum of orientation, communication, and coordination. Without accurate navigation and steady communication, long range was suicide. For Japan, whose radio components were increasingly built from substandard metals and recycled wiring, that system-level integration was impossible to duplicate. The conclusion was subtle, but brutal. The Mustang didn't just fly farther, it knew where it was, and how to get home. Doctrine and training. The culture of endurance. The next realization had nothing to do with machinery. As Japanese analysts reviewed captured U.S. operations manuals, they encountered a mindset alien to their own doctrine. In the American fighter world, range was a discipline. Calculated, practiced, drilled. Pilots learned cruise settings, leaned mixtures, and formation spacing to reduce drag for the entire group. They carried navigation checklists, fuel logs, and alternate return procedures. Japanese fighter pilots, by contrast, were trained for offense and sacrifice. Their curriculum emphasized aerobatic mastery and kill ratios, not sustained endurance or escort coordination. In 1942, that doctrine made sense. The Zero's unmatched agility and range made it king of the Pacific. But by 1944, the air war had become systemic. Formations of bombers, escort screens, radar control, and logistics. Heroic skill meant little if fuel ran dry over the ocean. A captured American manual read, "Escort is protection, not pursuit." That single sentence summarized what separated the two air forces. American pilots were rewarded for discipline, staying with bombers, holding position, conserving energy. Japanese pilots, pressured by a warrior code that valued individual valor, often broke formation to engage, burning fuel and leaving the bomber's path open for follow-up attacks. The engineers knew that even if they could build a Mustang clone, their doctrines could not sustain its advantages. Long range required patience, not impulse, teamwork, not glory. By 1945, the Japanese training system itself was collapsing. Fuel shortages limited flight hours. Many new pilots entered combat with fewer than 150 total hours, compared to American flyers with 400-600. Flying economically, navigating by radio, and escorting under formation discipline demanded an education Japan no longer had time to give. Range, they realized, was not only mechanical, it was cultural. Production and sustainment. The machine behind the machine. The final notebook section carried no sketches, only statistics. Japan's engineers compared national output figures and discovered a truth more devastating than any dogfight. Industrial range determined aerial range. To keep one Mustang flying, America produced a river of spare parts, fuel drums, and maintenance hours. Every component, from magnetos to spark plugs, was standardized, interchangeable, replaceable. A fighter could land damaged at Iwo Jima and return to Tokyo skies within days. Japan's aircraft, by contrast, were individuals, hand-fitted, delicate, often incompatible even within the same model batch. A broken pump might ground an entire squadron. Factories in the United States built engines, radios, and guns in different states, yet to the same tolerances. Trucks delivered them by the thousands. Japanese plants, bombed daily, produced in fragments. Wings here, engines there, final assembly under air raid alerts. Without stable electricity, machine tools rusted. Without alloys, pistons seized. Maintenance was equally constrained. Each Mustang came with a service manual thick as a novel, updated through a standardized supply chain. Japanese ground crews often improvised from memory. Even oil grades were mixed ad hoc. Every shortfall multiplied the range problem. Heavier wear, reduced efficiency, more fuel burned for less distance. In 1945, the numbers were cruel. The United States manufactured nearly 9,000 Mustangs. Japan built fewer than 4,000 high-performance interceptors of all types combined. And while American factories expanded through automation, Japan's were disintegrating under bombing and blockade. The engineers knew the difference could not be erased with ingenuity alone. It required a nation-sized infrastructure, something no amount of technical insight could substitute. By the time they finished their reports, the air outside their hangar vibrated daily with the sound of those same P-51s strafing Japan's airfields. Their measurements, once intended to bridge the gap, had become an epitaph for an era of aeronautical isolation. As their notes concluded, one final sentence appeared in the margin of a report now preserved in archives. "We have learned why the enemy reaches our homeland, and why we cannot reach his." That line leads us directly into the next phase. The climax, turning point, when the Mustang's range ceased to be theoretical and became the decisive factor in the final battles for Japan's skies. The missions that proved it on the morning of April 7, 1945, the tarmac at Iwo Jima shimmered under the equatorial sun. Rows of freshly assembled Mustangs lined the runways, their aluminum skins gleaming like mirrors, red and yellow squadron markings freshly painted. Mechanics moved like clockwork around them, checking fuel lines, oil pressure, and gun synchronization. In the command tent nearby, pilots studied maps of Japan spread across the table. The mission: escort the B-29s to Tokyo. Each man carried a single figure in his head, 1,500 miles round trip. It was not only a test of courage but of mathematics. The planners calculated mixture settings, propeller pitch, and climb rates down to the decimal. Every unnecessary minute of throttle could mean the difference between returning home or ditching in the Pacific. At dawn, the engines roared. The sound rolled across the island like surf. From above, the formation stretched into the horizon, waves of silver crossing into a deep blue sky. Beneath them lay 8 hours of ocean. 2 hours into flight, the Mustangs rendezvoused with the bomber stream, massive B-29 formations moving toward Honshu at 25,000 feet. For the first time, the superfortresses were not alone. Pilots in the bomber cockpits looked out their windows and saw slender fighters dancing in the sunlight beside them. The sense of security was electric. When the Japanese radar screens lit up, Tokyo's Air Defense Command expected unescorted bombers. Instead, they faced a combined armada. Hundreds of bombers with fighter cover that would not turn back. The scramble order went out across airfields in Kanto, Chiba, and Ibaraki prefectures. Ki-84 Hayats, Ki-61 Tonis, and J-2M Raidens clawed into the sky, burning precious fuel before even sighting the enemy. The first interception occurred southeast of Tokyo Bay. A handful of Japanese fighters managed to reach altitude and dive into the bomber stream, but their attacks were instantly met by Mustangs emerging from the sun. Major James B. Tapp of the 78th Fighter Squadron recorded the encounter. "They came up fast, maybe 10 or 12 of them. We turned into them and stayed there. Our gauges were still in the green. They had one pass, then they were gone. It was not a duel, it was an asymmetry." The Japanese interceptors, designed for rapid climbs and short bursts, had already consumed half their fuel. Once they dived to attack and climbed again, their gauges neared empty. The Mustangs, running at efficient cruise settings, still had hours left in their tanks. When the battle dispersed, the bombers continued unmolested toward Tokyo's industrial belt. Below, fires burned along Kawasaki and Yokohama. In the following weeks, mission after mission confirmed the pattern. On April 12th, Mustangs from the 21st Fighter Group escorted bombers all the way to the Nakajima Musashino plant, the same factory where engineers were examining a downed Mustang. Irony hung thick in the air. While Japanese technicians studied the secret of range, the living proof of it thundered above them. The 7 Fighter Command refined its tactics with each flight. At precise time intervals, the Mustangs dropped their external tanks, first the 108-gallon paper tanks, then the smaller ones, to maintain speed at altitude. Their endurance now covered the entire operational radius of the Japanese mainland. When returning, they often detoured along the coast, attacking airfields and trains. Japan's defense network crumbled under this new harassment. Nowhere within its own territory was safe. The U.S. Army Air Forces soon documented a sharp decline in B-29 losses. In January 1945, unescorted raids had seen losses near 4 to 5% per mission. By June, with regular Mustang escort, losses fell below 1%. The equation of air warfare had been rewritten. For Japanese commanders, the psychological toll was severe. The homeland, once their last redoubt, had become a battlefield under constant watch. Civilians grew accustomed to the shimmering trails of vapor that marked the Mustang formations overhead. The phrase, "enemy fighters over the capital," became a grim daily report. The engineers at Tachikawa, working in silence, listened to those same engines overhead and knew the data they collected on the captured P-51 was no longer theoretical. It was happening. Every number on their clipboard was flying above them in real time. The strategic consequences rippled through every level of Japan's war machine. Airfields were relocated, camouflaged, or abandoned. Interceptor squadrons hoarded what little aviation gasoline remained. The Imperial General Headquarters issued orders to conserve every drop of fuel for decisive homeland defense. Yet with every new raid, the Mustangs returned, unimpeded, undiminished. To the American pilots, the missions were long, exhausting, and often lonely. Endless ocean, thin air, and hours of tension. But each time they saw Japan's coastline appear on the horizon, they understood they were flying the aircraft that had made invasion possible. The Mustang had turned geography into vulnerability. In July 1945, as the B-29s shifted from precision strikes to area firebombing, the P-51s became hunters of opportunity. They strafed railways, barges, and airfields across Honshu and Kyushu. Japanese aviation fuel stocks dropped below 5% of pre-war levels. The engineers kept writing their reports, measuring propeller pitch and radiator ducting. But the war was already lost in the mathematics of range and endurance. Every mission proved it again. Whoever owned distance owned the sky. And soon, that truth would be confirmed not just in flight logs, but in the cold measurements taken inside that silent hangar. The captured Mustang on the bench, the hangar at Tachikawa Air Arsenal just west of Tokyo, smelled of fuel, sweat, and resignation. It was late May 1945. The capital had already been burned by waves of B-29s. The city beyond the airfield lay in ruins. Yet inside, under dim lights and scattered blueprints, a group of Japan's best engineers gathered around a battered P-51D Mustang, one of the few intact specimens they would ever see. The fighter had crash-landed weeks earlier after a long-range raid. The pilot had survived, captured, and interrogated, but the real interrogation was happening here, on the airframe itself. A guard stood by as engineers, dressed in stained overalls, began the autopsy of the aircraft that had undone their nation's air power. The first layer was reverence. They touched the skin of the Mustang as if it were a living thing. The panels were thin, yet strong, the rivet lines straight as if carved by machine rather than man. In contrast, Japanese aircraft, hand-fitted in cottage workshops, carried irregular seams, subtle warps, and millimeters of variance. The engineers could see it immediately. The Americans had built an aircraft to blueprint precision, not to individual skill. They removed the wings. Inside, the wet fuel cells, sealed with synthetic rubber and flexible enough to absorb vibration, astonished them. Their own fighters still used rigid aluminum tanks prone to cracking under stress. These self-sealing liners explained how the Mustang could carry internal fuel so safely over thousands of kilometers. They traced the drop tank connections, clean, standardized quick disconnect valves. No tools, no leaks. A mechanic connected and removed them by hand in seconds. Japan's own external tanks required improvised fittings and manual priming, wasting both time and fuel during emergencies. Then they studied the radiator system beneath the fuselage. One engineer, a young graduate from the University of Tokyo, ran his hand along the curved duct and whispered, "It makes thrust." He was right. The Meredith effect, by which hot air from the radiator was expelled rearward at such velocity that it produced a small jet-like push, had never been fully replicated in Japanese aircraft. The concept was known, but the machining precision and design integration were beyond reach. When they unbolted the Merlin V1650 engine, the room fell quiet. The two-stage supercharger gleamed like something alien. Its gears meshed perfectly, each tooth polished to tolerance. They measured clearances, fractions of millimeters, and realized what that meant. Every engine, every Mustang, could perform identically. That kind of consistency required industrial stability. Japan's bombed-out factories and scattered subcontractors could never sustain it. A senior officer from the Army Aeronautical Technical Research Institute recorded the findings in his notebook. His tone was factual but weighted. The structure and range advantage of the enemy's aircraft are not the result of one exceptional device, but of a harmonious union of design, materials, and production control which we cannot achieve under present national conditions. The younger engineers looked crestfallen. For years they had believed that superior craftsmanship, the touch of the artisan, could balance Japan's lack of resources. Now, in the cold light of war's end, they saw the opposite. Mass precision had defeated art. Outside, the air hummed with distant engine noise. They paused their work and listened. The sound, a steady, low-frequency growl, was unmistakable. Another formation of Mustangs was passing overhead on its way to strafe an airfield in Chiba. The irony was unbearable. The same type they were studying, bolt by bolt, was attacking their own homeland in that very moment. They turned back to the machine. One engineer began sketching the fuel control system. Another diagrammed the cockpit layout. The pilot's visibility was exceptional. The controls, logical. It was not a warrior's cockpit. It was a technician's. Everything served efficiency. Navigation compass perfectly aligned with sightline. Throttle quadrant labeled for fine mixture control. Instruments grouped by function. One mechanic murmured that this airplane seemed to think like its pilot. It wasn't faster in every dimension, but it was smarter. As they concluded their examination, a somber consensus emerged. Japan could copy the Mustang's outline but not its essence. The alloy composition of its rivets, the uniformity of its bearings, even the synthetic rubber in its tanks depended on resources Japan no longer possessed. Its aviation fuel, its lubricants, its machine oils, all inferior, all rationed. And without the industrial ecosystem that birthed this machine, imitation would be futile. That evening, the lead engineer drafted a final report addressed to the Ministry of Munitions. It ran 12 pages, technical yet painfully honest. The final paragraph read, "Even if exact replication were possible, the performance could not be realized without equivalent quality of gasoline, alloy, and production accuracy. The P-51's range is not the product of one device, but of a civilization's entire industry aligned toward endurance." When the war ended 3 months later, that report was found among stacks of incomplete prototypes. The captured Mustang itself was destroyed in a bombing raid, reduced to molten aluminum. But its influence survived in silence, in the minds of those few engineers who had seen it up close. They would later tell Allied interviewers during occupation research, "We admired it not for its beauty, but because it taught us our limit." And that limit had already rewritten the air war. The same aircraft that they dissected piece by piece had, in the skies above, ended the age of the zero and sealed the fate of Japan's empire. Consequences in the air and on the ground. By June 1945, Japan's sky had changed color. The deep indigo that once hid formations of zeros was now cross-hatched with white contrails drawn by thousands of Allied bombers and their escorts. The air war had entered its final merciless arithmetic. Each morning, radar operators on the coasts of Kyushu and Honshu tracked new streams of dots moving east to west, the B-29s. But what chilled them was not the bombers themselves. It was the thin slivers of light that accompanied them. The P-51s were there every time, high above or weaving ahead, waiting for any sign of interception. Japan's airfields became traps. To scramble was to die. Fighter losses mounted catastrophically. Squadrons that once fielded 30 aircraft now counted 6 or 7 flyable machines. Fuel deliveries were measured not in barrels but in buckets. Many interceptors never left the ground because their aviation gasoline had been requisitioned for the last operational defense units around Tokyo. Maintenance crews scavenged spark plugs from wrecks. Pilots taxied with engines coughing on a mix of alcohol and pine root oil. Meanwhile, the Mustang units from Iwo Jima matured into hunters. Their mission briefings expanded beyond escort. Airfield suppression, rail interdiction, shipping strikes. With each sortie, Japan's infrastructure bled. The once formidable network of island bases that had projected Japanese air power now served as waypoints for American domination. The pattern of attacks evolved with grim efficiency. At dawn, Mustangs swept ahead of bomber formations, diving on airfields like Tachikawa, Atsugi, and Kagamigahara. They destroyed parked aircraft, strafed fuel depots, then climbed to rejoin the bombers. When the B-29s turned home, the Mustangs lingered, striking rail convoys and warehouses. This rhythm left Japan's pilots no rest. Even on the ground, the enemy's range reached them. Civil defense observers noted a new psychological phenomenon. The sound of a single Mustang could send entire towns running for cover. Its engine tone, sharper than any radial's growl, became the acoustic emblem of defeat. Inside command bunkers, staff officers studied sortie reports and realized the cruel symmetry. Every gallon of American fuel reached the front line. Every drop of Japanese fuel was consumed in the act of merely climbing to meet it. Strategic defense had inverted. Geography, once Japan's shield, now magnified its exposure. The statistics confirmed what eyes already knew. Between April and August 1945, U.S. fighters destroyed over 4,000 Japanese aircraft in the air and on the ground, most without significant loss. The B-29 campaign's effectiveness multiplied as interception rates fell by half. By July, some raids encountered no opposition at all. The psychological weight of this collapse fell heavily on the remaining defenders. Veteran pilots, once national heroes, now described their missions as suicide without ceremony. They flew knowing their engines might seize before contact, or that landing strips might no longer exist when they returned. Every sortie became an act of symbolic resistance. Brave, but strategically irrelevant. For the population below, the change in the sky mirrored the change of fate. Children in Tokyo learned to identify Allied aircraft silhouettes by sound. Mothers kept buckets of water near doorways for the inevitable fires. The once mystical idea of Japan's invincibility dissolved in the daily thunder of P-51s and B-29s overhead. Back at the air arsenals, the engineers who had examined the captured Mustang followed the reports grimly. Each new loss confirmed their findings. Technological truth had translated directly into battlefield outcome. Range had become destiny. In one late-war memorandum from the Army's Air Technical Division, a single sentence summed up the national exhaustion. We can no longer defend the air, only endure its occupation. That endurance would not last long. The last summer of the war was approaching, and with it, the reckoning for both the machines that ruled the sky and the men who built them. Records, reports, and post-war assessments. When Japan surrendered in August 1945, the victorious Allies entered a world of paper, a labyrinth of files, design drawings, and half-finished prototypes. At facilities like Tachikawa, Yokosuka, and Kakamigahara, investigators from the U.S. Army Air Technical Service Command found crates of documents labeled P-51 Study or Enemy Aircraft Comparative Analysis. Among them were the handwritten notes of the engineers who had once circled that captured Mustang. Their findings astonished the Americans not because of what they got wrong, but because of what they got right. Even amid shortages, bombing, and collapse, the Japanese engineers had dissected the Mustang with surgical accuracy. They understood its principles, its integrated systems, its aerodynamic efficiency, its industrial foundation. They simply lacked the means to reproduce it. In one recovered report, a Japanese officer had drawn a triangle labeled range, Ketawi engine plus fuel plus manufacture. Below it, he wrote, "Deficiency in any side collapses the figure." It was both an equation and an epitaph for Japan's aviation program. Post-war Allied interviews deepened this respect. Engineers who had studied the Mustang during the war were now debriefed under the supervision of the U.S. Strategic Bombing Survey. They spoke candidly, no longer bound by military secrecy or illusion. One recalled, "We admired the aircraft more than we feared it. It showed us that endurance was a science, not a gamble." American officers, for their part, recognized the thoroughness of their former adversaries. Many of the Japanese evaluation reports were translated and circulated among U.S. aviation circles as examples of technical intelligence under extreme conditions. They were clinical, disciplined, and, in a haunting way, full of admiration. Meanwhile, the Mustang's wartime performance was quantified in cold numbers. Over the Pacific, P-51 units had flown nearly 15,000 long-range escort and strike missions, claiming over 4,900 enemy aircraft destroyed in air and ground action. Average mission range, 1,350 miles. Average operational readiness, over 85%. No other single-engine fighter of the war matched that. Combination. For Japan's post-war aviation industry, when it was finally permitted to revive under civilian oversight, those wartime lessons became templates. Engineers who had once studied the Mustang went on to design peacetime aircraft for companies like Mitsubishi, Fuji, and Kawasaki. They remembered the Mustang not as an enemy weapon, but as a masterclass in integration, how structure, engine, and fuel worked as one living system. Several later contributed to the YS-11 airliner project in the 1950s, Japan's first post-war passenger plane, where precision manufacturing replaced the improvisation of wartime desperation. American engineers, too, absorbed the wartime lessons. The Mustang's long-range success validated the idea of global reach, a philosophy that would evolve into jet-age doctrine. From the P-51's lineage came the F-86 Sabre, then the F-100 Super Sabre, and eventually the F-15 Eagle, all embodying the principle first proven over Tokyo. Endurance is power. Historians studying the closing months of the Pacific War often frame the B-29 raids as the decisive factor, but the quieter truth is that the P-51 made those raids possible. Without Escort, the bombers would have suffered the same attrition that crippled earlier campaigns in Europe. With it, the U.S. could strike Japan daily with precision and impunity. That consistency broke Japan's industrial heart before the atomic bombs ever fell. In 1947, a declassified U.S. report summarized it bluntly. The effectiveness of the Pacific strategic bombing campaign was contingent upon the operational radius of the P-51 Mustang. Once that factor was achieved through Iwo Jima, Japanese air resistance collapsed. In Japan's own archives, the tone was equally sober. A Ministry of Munitions memorandum from late 1945 stated, "The defeat of our air forces was not due to lack of courage or skill, but to systemic inferiority in fuel quality, manufacturing precision, and range efficiency." No bitterness colored those words, only clarity. The engineers who had once worked by lamplight among the ruins now helped rebuild a peaceful industry, carrying within them the lessons of that single captured aircraft. The Mustang they studied no longer existed. Its pieces had been melted and repurposed. But its impact endured, in the notebooks that survived, in the new generation of engineers it inspired, and in the understanding that the measure of an aircraft is also the measure of the civilization that builds it. And from those ashes, Japan would rise again, not as a maker of weapons, but of precision machines that would one day equal, and even surpass, those that once humbled it. The range of a civilization. When the Mustang first appeared above Japan, it was more than a fighter. It was a messenger. It carried within its wings not only fuel, but the accumulated logic of an industrial democracy at full stride. Precision engineering, standardized manufacture, efficient logistics, and the belief that systems, not individuals, win wars. The Japanese engineers who studied the captured P-51 were among the first to understand that the war's outcome had been written in assembly lines long before it was fought in the sky. They discovered that range, the ability to reach, to endure, to return, was not a mechanical gift but a reflection of a nation's organization, its material science, its discipline. The Mustang's 1,600-mile radius was therefore symbolic. It measured not only fuel and horsepower, but the distance between two worlds of thinking, one industrial and procedural, the other artisanal and instinctive. Japan's craftsmen had built beautiful machines. America had built a system that made performance repeatable. In the crucible of total war, only one model could survive. And yet, the story ends not in humiliation, but in inheritance. The same Japanese engineers who once admitted defeat in range would, decades later, design aircraft, cameras, and automobiles that conquered global markets with the very precision they once lacked. They had learned from the Mustang that technology is not conquered by pride or courage, but by process. In museums today, the P-51 stands gleaming, restored, polished, admired. Few who see it realize that one of its greatest victories happened not in combat, but in the quiet of a hangar, where its defeated enemies measured it piece by piece and glimpsed the future through its design. From that revelation grew a new Japan, disciplined, industrial, precise, a nation that turned the study of its own defeat into the foundation of its rebirth. And so, the range of the Mustang endures, not only in miles, but in meaning. It was the measure of what humanity can achieve when endurance becomes not merely a tactic, but a philosophy.